Welcome to the beaver's balance. Here, a steady stream meets an intricate dam of logs and vines, built with perfect symmetry so the weight on one side matches the other. When we solve a system of linear equations, we are trying to manage two separate mathematical rules at the exact same time. We need to find the specific point where both rules are true. By bringing these equations together into a system, those two separate rules merge into a single shared constraint. Finding that shared truth is the entire goal. Mathematical balance means satisfying simultaneous conditions, keeping both sides equal without breaking either rule. This grid shows two rules mapped as paths. First, y equals x plus 1 is a heron's trail with a positive slope. Second, y equals negative x plus 5 is a beaver's downward path with a negative slope. They intersect exactly at 2, 3. That coordinate is the single point on the entire grid where the heron's path and the beaver's path overlap. It is the only mathematical solution that makes both equations true at the exact same moment. This physical balance scale shows how we can solve that same system algebraically. Because both expressions equal y, we can set x plus 1 equal to negative x plus 5. To find the value of our unknown variable, we use a simple rule: do the same to both sides. By adding one x bundle to both sides, the scale stays balanced, giving us 2x plus 1 equals 5. Next, we remove one loose reed from each side. This leaves 2 x bundles on the left and 4 loose reeds on the right. Dividing the remaining piles evenly shows that a single x bundle equals 2 individual reeds. Now, pause the video for a moment. Try plugging x equals 2 back into either of our original equations to find the value of y. Using either equation, substituting 2 for x yields a result of y equals 3. This gives us the coordinate pair 2, 3. Whether we trace the intersecting paths on a graph or isolate the variable on an algebraic scale, we arrive at the exact same coordinate. Both methods locate the point where the system's shared constraint is perfectly balanced. Here is a different system: y equals 2x plus 1 and y equals 2x minus 3. Otters swim down side-by-side streams. Both equations have a slope of 2, sharing the same rate of change. With different y-intercepts, these paths extend infinitely without merging. Parallel paths never cross. Without an intersection, there is no single point that makes both equations true, meaning this specific system has no solution. This split-screen summary shows our three scenarios side by side. An ordered pair only works as a solution if it perfectly satisfies every equation in the system at the same time. Mastering how to find that shared truth gives you the exact tools you need to tackle complex algebraic constraints and build accurate linear models of the real world.